In this unit, which I'm calling Basics, or subtitled Remembrance of Things Past, we'll look at some of the basic ideas that are needed for the rest of the college algebra course. We'll look at numbers, which you can think of as the raw materials for the course, but they are not what the course is about. The course is really about the operations that you perform on numbers. We'll look at the language of mathematics a little bit. We'll look at exponents and exponent notation. We'll look at polynomial expressions, and we'll finish up with a little bit of geometry. So I hope you enjoy it, and here we are. The first part of basics we'll look at are numbers. And under numbers, the first thing we'll look at is an idea of mathematics that will help us describe numbers. We'll talk about sets of objects, first of all. So let's look at that. Sets of objects. Now, sets are what a mathematician calls a bunch of things. Now, what will be in such a set, or a bunch, or a collection? Numbers, expressions, functions, all these things that we'll be talking about later in the course. But let me go ahead and give you an example. For example, let's look at the set of base 10 digits. Those are the digits we use to write all of our numbers in our numeral system. And I'll give you the notation as we go. I'll use this curly brackets or braces to start the set, and then I'll list all the digits inside with commas. So we're 4, 5, 6, 7, 8, and 9, and then end the brackets. So these beginning and ending items are called set brackets. Sometimes they're called braces. And they are what indicate the beginning and the end of the set. All of the elements of the set, there are so few of them, I can simply list them. All the elements are separated, as you see, by commas. This is an example of a finite set. It's a set with only a finite number of elements. In fact, you can see that there are exactly 10 elements. And what we've done is we put it all together in one place. It's a collection of objects. That's all that a set is. Nothing fancy, just a simple idea. Let's look at a couple more examples. Here's an example. This should be familiar to anyone that speaks English. The set of 26 English letters. I will write that starting off with the braces again, and then list the letters A, B, C, and D. And you know, there are so many that I don't want to list them all. So what I will do is I will put dot, dot, dot in the middle, and then a comma, and then I will list the last few, X, Y, and Z. These dots, sometimes referred to as an ellipsis, is a way of indicating that the set continues on, and in this case I happen to know the ending, so I can put on the last few elements. This again is another finite set. Now, as you might expect in mathematics, there are lots and lots of sets that are not finite. We call those infinite sets. So let me give you an example of one of those, and yet again show you this notation. Example. Here is another set. This is the set of positive even numbers. Now, as we go on, we'll talk about numbers in detail, but I think you probably remember what these are. Numbers like 2, 4, 6, 8, 10, etc. Now you see, I put the dots at the end and I put nothing afterwards. I don't know how it ends because there's an infinite number of even numbers. There's always more beyond wherever I stop. So this is a perfect example of an infinite set. And this is one way of writing down such a set. We will learn other ways as we go. But I wanted to show you both finite and an infinite set. Now there's one more idea that we want to touch on before we start talking about numbers. And here I'll show you in an example what I mean. Here is a small set, the set 2, 4, 6. There's a set with only 3 elements in it. This is what's called a subset of that larger set we saw on the other page. 2, 4, 6, 8, 10, etc. The infinite set of real even numbers. You see that these 3 elements are contained in this set. This is a smaller set. This is a subset of the larger set. So if you were to look at this in a picture, say, If this shape describes the set, then what we have here is a small part of that set called a subset. Now, I will use that terminology throughout the course, and if we need to say anything more about sets and sets of objects, we'll introduce that terminology as we go. But now let's go back to the list and see what kind of numbers we will first look at. We'll first look at natural numbers. These are sometimes called the counting numbers. What are they? Natural numbers. These are numbers that we really take for granted. These are numbers that we didn't have to invent as we have had to invent other numbers. These numbers can be thought of as just existing. They are often denoted, the set is often denoted by a boldface N, and that's the way I'll write that. And what is this set? Well, it consists of these numbers, 1, 2, 3, 4, etc. And then sometimes we do this also. We'll put an N here to indicate the variable that I will use, or the letter I will use to stand for such numbers, and then a comma and continue on out to infinity. So this is a commonly used variable for natural numbers, and I'll use it from time to time. These will be taken as given. These are not invented. There's nothing to describe. These are simply the starting place for the number systems we will look at. But you know, there are lots of numbers within this set of numbers that are quite interesting. So let's go ahead and talk about a few of them, because they will have bearing later. There's a set of numbers that are called prime numbers. Now, why would I want to talk about those? Well, as in chemistry, it is helpful to look at what you might consider the atoms of the material that you are discussing. Prime numbers can be considered the atoms of the natural numbers. For example, let me go ahead and define what a prime number is. P is prime, call it a prime number, if, well, first of all, P is greater than 1, because 1 is not considered a prime number, and what makes a prime number an atom? P is divisible only by two things. Only by 1, which divides into every number, and itself, P. What do these numbers look like? Well, I'm sure you've seen these in your life. The set of prime numbers looks like this. The first one is 2, which happens to be the only even prime number. Then 3, 5, 7, not 9, because remember 9 would be 3 times 3, 11, 13, 17, etc. There are an infinite number of primes, and this is what they look like. Numbers like this. They're only divisible. They can only be factored, words that I will be describing soon, into themselves times 1. So those are prime numbers. Now with prime numbers, since we can think of them as the atoms of the natural numbers, you might expect that we ought to be able to write all natural numbers in terms of prime numbers. And so we can. And this is such a famous result, I just want to go ahead and introduce it to you. It's called the fundamental theorem of arithmetic. Arithmetic, you may ask. Why are we studying arithmetic in an algebra course? Well, as you'll see, it really is going to be the basis for much of what we do. And it's probably a theorem that you haven't seen in this form, but I think you know what it's going to say. Any natural number, that is to say, any of those counting numbers we saw before, any natural number can be factored. Now, I haven't officially defined the word factor, but a factor is simply a thing that is multiplied. So to factor a number like 12 would be to write it as a product of two other numbers. It can be factored uniquely. There's only one way you can factor it, and that one way is except for the order of the factors, because as you may remember from your knowledge of the numbers, that numbers like 2 times 3 are the same thing as numbers 3 times 2, into a product of prime powers. Prime numbers, prime powers. So, to say this one more time, any natural number can be factored uniquely, except for the order of the factors, into a product of prime powers. Now let me give you some examples so you'll know what it is I'm saying here. And once I do, I think you'll see that this is familiar. Let me take the number I mentioned a moment ago, 12. 12, as you know, can be written as 3 times 4. That may be the first thing that comes to mind. But 4 can be written as 2 squared. So this can be written as 2 squared times 3. Now 2 is a prime number, 2 a power. This is 2 times 2. That's what the 2 up there means. And 3 is another prime number. Let me do a few more examples. 70 can be written as 2 times 5 times 7, for example. 111 can be written as 3 times 37, etc. All the natural numbers can be written as products of prime numbers or possibly powers of prime numbers. And as I said before, and we'll define it again in a little bit, factors are things that are multiplied. Now before I leave this topic, I don't want to mislead you. Generally, factoring numbers is hard. If you start with a very large number and you try to factor it, it is very hard to do. In fact, that's being used in security systems these days for that very reason. But the kind of factoring we will do is fairly simple. And so I'll pause now and give you a chance to remind yourself of a few things. Now we'll continue our development of the numbers by looking at integers. So what are the integers? The integers is a larger set than the natural numbers. The integers are often denoted by a capital Z. You may say, what does that have to do with integers? There's no Z in the word integer. Well, just for the historically minded among you, this comes from the German word Zahlen, which stands for numbers. So that's what the symbolism comes from. And what are the integers? How do they differ from the natural numbers? Well, the way I'm going to define the integers is to give you a sense of why one would need the numbers. So let's imagine that we're moving ahead in the course here and we want to solve a certain very simple equation. Suppose we want to solve the equation x plus 1 equals 1. We want to find a number x that will make this equation true. Well, you know from your own experience that there is only one number that will make this true. We need what? We need the number 0. But in the natural numbers, there is no 0. So 0 has to be added to that, and that will become one of the integers. Let me show you one other small equation to suggest why we need another set of numbers. Suppose we want to solve x plus 1 equals 0 using that new number 0. Now from what you know, what would you have to add to 1 to get 0? Well, you'd have to add, we need a number like minus 1. But again, the natural numbers don't have any negative numbers in them. So we have to add these numbers in. So when we add them all in, we're going to get a set that is the integers. Here is that set, the set Z, and it will be infinite in both directions. So I'll have to start off with dots, and then I'll give you a few of the numbers, minus 4, minus 3, minus 2, minus 1. Then there's that special number 0, so I'll put it on its own line alone. And then we'll continue 1, 2, 3, 4, etc. out to infinity. Now there's a more compact way to write this, so I'll show you that. If we put 0 at the front, and then we put a plus and a minus sign here for 1, so we can imagine plus 1 and minus 1 being next to each other. And then plus or minus 2, plus or minus 3, plus or minus 4, etc. out to infinity. Now this is just more compact. So this is a more compact way of writing this set. But we have now expanded our set of numbers. We no longer have simply the natural numbers. Notice that the natural numbers are right here. They're included in the integers. We have added 0 and we've added all these negative numbers. And a reasonable way of describing the reason for that is to say that we need it to solve certain kinds of equations. So let me show you a couple of things in an example. about these numbers. These are things that you probably have seen much of your life. I'll just remind you of a couple of things. For example, if I take 0 times 5, now notice I've already started introducing a notation that you may not be familiar with. I'm using a dot for multiplication. Again, I will talk about that a little bit later on. But you can see that I'm multiplying 0 times 5. Well, you know what happens when you multiply a number times 0. You get 0. So there's a fact from your past, I hope. And if we take 0 times 82, we're going to get 0. It doesn't matter what number you choose. 0 times that number is 0. What else can we say? How about 0 plus a number, like 0 plus 7? Well, that is 7. The 0 contributes nothing. So you know that adding 0 to any number will result in the original number coming back. How about negative numbers? What are some of the properties you probably have seen before? Well, suppose we take two numbers like -5 and -2 and multiply them together. Well, you'll get 10. In fact, you get plus 10 because a negative times a negative is a positive. What about an addition problem? Take -5 plus 2. Well, as you know, 2 minus 5 will give me a -3, etc. So the kinds of facts that you should be familiar with are the facts about the elementary integers and the properties they have. So let's go ahead and look at another set of numbers that is built from integers. So we'll go back to my list, and after integers we will look at rational numbers. This is where we take integers and we create a new set of numbers. And I'll show you exactly how that's done. Rational numbers. Now, rational numbers have their own bold-faced letter symbol, Q. And this time the Q stands for quotient, so that seems to make good sense. What does a rational number look like? Well, they're what you previously called in grammar school fractions. P over Q. That is a rational number. What are the P and Q? The P and the Q are integers. So they come from that set Z that we saw a moment ago. And we also say that Q is not 0. Now we're forbidding the bottom to be 0. The bottom of the fraction is not 0, and I'll explain why in a little bit, but we're going to say that division by 0 is not allowed. It is undefined. There's a good reason for that. But this, of course, is what you called before, as I said, a fraction. You might also have used the word ratio, which is where rational comes from in the description of these. And now let's look at a few examples, just to remind you what we're talking about here. Examples, you know what these are: 1/2, 2/3, 11/13, 574 over 201, etc. Those are all examples of rational numbers. They're fractions. Some of them, as in the case of the last one, are improper fractions. The top is bigger than the bottom, but they're still rational numbers. Now, let me note that once again we have increased our number system without losing anything. All n is in Q. In fact, all z, the integers, all of that set is in Q. How do I know that? Well, since if you take a number n from either z or the natural numbers and you put it over 1, lo and behold, you have a rational number. But of course n over 1 is still n, and so these numbers from here can be rewritten as n over 1, and they appear as rational numbers. And for example, 8 over 1, of course, is 8, and so on. So that's what rational numbers look like. Now, I said a moment ago that division by 0 is not allowed in the rational numbers. So let me go ahead and give you that warning and give you a reason why that is true, so that we don't have any mysteries here. Warning: division by 0 is what's called undefined. Now you might say, well, it's undefined. Why doesn't somebody define it? Well, there's a reason it's undefined, because you cannot define it as a number and end up without a contradiction. So the answer is why. The question, rather, is why. Why is it undefined? Here's why. Let us suppose Let's take a simple case, because if it fails here, it's probably going to fail for the rest. Suppose 1 over 0, and I'll put it in quotes, suppose 1 over 0 is taken to be a number. Well, if 1 over 0 is taken to be a number, it must share all the properties that the other numbers we've seen satisfy. That is going to lead us to a problem. Watch. Then, consider the following situation. And this is just one of many possible situations I could describe. Consider the following. 0 times this new purported number 1 over 0. Now, I can make two different arguments. On the one hand, I can say this must be 0. Why? Here's my reason. Since, as we saw a moment ago, 0 times x equals 0 for any number that we've seen, x. You multiply a number by 0, it is 0. That's what I've done here. Multiplied this purported number by 0. So I claim it's 0. Fine. On the other hand, I can also make the following argument, that this is equal to 1. And what's my reason there? Since, copying what I have here, if you have x times 1 over x, that's the same as x over x, and of course that's 1 for any x. Well, now we have the contradiction. If I assume that you can divide by 0 and that 1 over 0 is a legitimate number, then I end up with it being multiplied by 0. I get either 0 or 1. I can't have both. So there's no way, no matter what I define this to be, I will end up with a problem like this. That's a contradiction. So 1 over 0 can't be defined, because if you define it, you're going to have contradictions arise, and you don't want that in your number system. So, in case anyone was wondering why division by 0 is not allowed, there's the reason. All right, let's look at some operations on rational numbers, and I'll say some operations on Q. And these are fraction operations. These are the kind of things you've had experience with over the course of your elementary school career. But now we'll put them in a form that's more algebraic. For example, suppose you have the fraction a over b times another fraction c over d. What does that simplify to? How do you multiply two fractions? Well, this is the easiest of the operations. This one's easy. You multiply the top, ac, and over the bottom, bd. Now, there are a couple of things going on here with notation that we'll have to discuss later. I'm using the dot here again for multiplication. And also over here, I'm using nothing. I'm just putting the numbers next to each other for multiplication. So I have AC over BD. What about division? What if I took the fraction, or rational number A over B, and I wanted to divide it by the fraction, or rational number C over D? How is that done? Well, this is how it's done. You just copy over the top one, A over B, and then we're going to multiply it times the bottom one, but we're going to change the bottom one to what's called its reciprocal. Now that's a fancy older word. It just means flip it over. So if it's C over D here, we'll multiply it by D over C. And then of course this looks just like the case above, so this becomes AD over BC. And that's how you divide two rational numbers. The top one just stays, the bottom one comes over, multiplies, and gets flipped over. So that should be something that you've seen before. And we've covered two operations now, multiplication and division. There are two more. There's the addition and subtraction. So let's just go ahead for the sake of completeness. Let's look at A over B plus or minus C over D. Now, of all of the operations, this is the hardest. These are the hardest. Because the reason is that A over B and C over D are divisions in themselves. And pluses and minuses are a different kind of operation. So we have to decide how we're going to do this. And the way that this is done is we get what's called a common denominator. We make the fractions have the same number at the bottom. And the easiest way to do this is to take A over B, multiply it by whatever I need on the bottom, and I'm going to take the product of these two numbers as my new denominator. So I need a D down there, And since I don't want to change anything, I'll multiply a over b times d over d. Remember, d over d is 1, so I don't change anything. Then plus or minus. C over d, I do the same thing, except I multiply by b over b. The advantage is now the bottom is bd, and the bottom is bd here. So I will get a new fraction with a denominator or a bottom, bd, and the top will be ad plus or minus bc. And that is how you add or subtract two fractions. This number at the bottom here, by the way, is often called a common denominator. There's one of those older words. Denominator. We'll just call it bottom for the most part. And likewise, we'll refer to the tops of the fractions instead of numerators. We'll call them top most of the time. All right, let me go ahead and do a few numerical examples just to give you a chance to warm up a little bit. Example, if I take 2/5 and I divide it by 1/7, remembering the process, I copy down 2/5 and then I multiply it by this fraction flipped over. That's 7 over 1. And so I will have 14/5. And so I've divided two fractions and ended up with another fraction. Similarly, I can do a simple addition, maybe take 1/3 plus 1/5. I take the 1/3, I multiply the top and bottom by 5 over 5, plus 1/5, multiply top and bottom by 3. So my denominator will be 3 times 5, or 15 in both cases. I have a new fraction, the bottom is 15. The top is 5 plus 3. So I end up with the fraction 8/15. Now you'll have a chance in a little bit to practice some of this, but these should be simple operations, I hope. Another note I want to make before we have a chance to stop. Note, in this example, I will illustrate another idea. Suppose you're faced with the fraction 4/6. Well, that is more complicated than it needs to be. If you recognize that there's a factor common to the top and the bottom, you can then remove it as follows. If you realize the top is 2 times 2 and the bottom is 3 times 2, and of course here's where factoring comes in if you can do it, you see that what you've got is a new fraction here, 2 over 2, which is just 1. So this can simply be rewritten as 2 over 3. This is nice because now 2 and 3 have no factors in common. They are in fact prime numbers, and that's a much nicer fraction than the original. And when you do this, this whole process is called put into what's referred to as lowest terms. Put this into lowest terms. And that just means you find out if they have common factors, the top and the bottom, and you rewrite them. And those common factors, it's called canceling, but of course you realize it's just rewriting 2 over 2 as the number 1. All right. One final note for rational numbers before we move on to the next set of numbers. My final note here on rationals is do not, here I'm going to give you a stricture, do not use mixed numbers or mixed number notation. This is a notation that's very common in the elementary schools, like, for example, 3 1/4. And I'll tell you why. Because 3 1/4 means 3 plus 1/4. That's what you mean when you write down 3 1/4. You mean 3 plus 1/4. But now, when we write numbers next to each other, we're assuming for the most part multiplication. So we don't want to use this notation, and so I highly recommend that you do not do that. It's an older notation, and I would suggest that you simply ignore it and use another form. All right, let's go back to my list and look at one last set of numbers before we take a pause. The last set of numbers are the irrational numbers. So let me write that down, the irrational numbers. Irrationals. Irrationals. These are ones that are not rational. And let me again give you a reason by presenting you with a simple equation that will require an irrational to be solved. if you want to solve a very simple equation like x to the power 2 equals 2. So I'm looking for a number here that when multiplied by itself, that's what the 2 means, I get 2. But there are no natural numbers lower than 2 that will have that property. The only natural number less than 2 is 1, and 1 times 1 is 1. So if I'm going to find a number, it's outside of my system. What do we need? Well, you may remember the notation that's used for this. We need either plus or minus what's called the square root of 2. And you may notice the way I write this with a little tail. I'll remind you of that later. But this is a number that when squared gives me 2. This number is not an integer. It's not a natural number. It's not a rational number. It is a new number. We must add it to our set Q, which was the last set of numbers we were looking at. What other kinds of numbers might not exist in 2? Well, the set of irrationals is rather large. And it's a mixed bag. It's really a motley bunch of numbers. Square root of 2, square root of 3, another famous number you may know, pi, another number from that arises in calculus, e. These are all examples of irrational numbers. They are oddballs, if you like. They are not defined as quotients of other numbers like rational numbers. In fact, they're not defined in a direct manner at all. They're simply all the numbers that are left over when you've picked out the rational numbers. There are a lot of them. In fact, let me just give you one little fact here. In fact, there are, surprisingly, there are more irrationals than rationals. These very odd, strange numbers that don't seem to fit any pattern here. There are, in fact, more like that than there are rational numbers. Now, I won't go into that here, but on that note, we'll pause, and you can explore the number systems we've already looked at. Now that you've had a little practice with rational numbers and the other numbers we looked at earlier, we'll now put them together with the irrationals and produce a set called the real numbers. So let's examine that. The real numbers also have a symbol that's very common. They will be often denoted by a capital R, bold-faced R. Oh, and one thing while I'm here, real numbers. These numbers are no more or less real in the colloquial sense than any other number. All numbers are equally real. This is simply a technical term. Let me put that up here. This is a technical term that we use to describe the set I'm about to describe. So there's nothing more real about these than any other numbers. All right, what is the set of real numbers? Well, it is the set that contains Q, and Q, remember, is the rational numbers, and all the irrationals. So you take all the rationals and all the irrationals together, and that forms what we refer to as the set of real numbers. Now, this is the primary set that we are going to be looking at in college algebra. This is the set we'll spend most of our time in. Now, let's go back to my list, because there's a way of talking about these numbers that is quite nice. It takes advantage of geometry. The real line, from numbers to points. So we're going to take numbers, which are in the realm of arithmetic and algebra, and connect them up with a geometric idea. This will be called the real line. So here's what we're doing. Give you the overall view. We're taking a geometric object, points, all right? Points which lie on a line. And we are going to put them in what's called a one-to-one correspondence with the real numbers. And real numbers, of course, are an arithmetic or algebraic object. So we're connecting up algebra and geometry here. And it'll be very fruitful when we have them connected. It'll be easy to see one idea from the other. So let's go ahead and write down what the real number line looks like. It is, of course, a line. So here's a line. And I'll put little arrows at the end so I indicate that this goes on forever in both directions. Now, as it stands now, it's a geometric object with points. What I'm going to do now is start labeling the points so that it gets algebraic notation connected with it. So the real numbers become labels for the points on this line. First of all, I'm going to label what you might consider the center of the real number system, the number 0. The numbers go to the right and to the left from there. The rightward direction gives you positive numbers. The leftward direction gives you negative numbers. Now 0 I will place anywhere. So I'll even mark that down, anywhere. Let me also point out that this is also referred to as the origin. So you can think of it also as the origin, the place where all the numbers sort of begin. Then, arbitrarily, I will pick a distance, say to the right, and I will mark that as my 1 unit distance. So this is an arbitrary 1 unit. I just make a choice. But once I have that, I can now put all the other real numbers on here without any difficulty. Using that as my measuring device, I can say then that 2 will be there, 3 will be there, 4 will be there, and so on. In the other direction, -1, -2, -3, and so on. And you might say, well, where are all the other numbers? Where are, say, the rational numbers? Well, we just need to label them. Between 0 and 1 at the halfway mark is probably a good place to put the number 1/2. If we went a little further, beyond 1, we might find a place for, oh, the number 10/9, say. And where would square root of 2 be? Well, square root of 2, as it turns out, would appear in about there. Square root of 2, the irrationals also live on this line. What about in the negative direction? Well, down here somewhere maybe is the number -13/11. And so on. All the numbers we've seen, the rationals, the natural numbers, the integers, and the irrationals can be considered lying along this line. And just to emphasize what I said about direction, let me write 2 large arrows here. There's one going to the right. Here's another one going to the left. The one to the right, I'll write right in there. And right means what? It means increasing. So as you move toward the right, no matter where you start, even if you start over here, you move from -3 to -2, you've gained by 1. As you move to the right, you gain. As you move to the left, that is decreasing. The numbers go down as you go to the left. So if you move from 2 to 1, it's gone down. But if you move from -1 to -2, you've also gone down by 1. So you have left and right. All right, let's go back to my list and we'll talk about another aspect of the real numbers. We looked at real numbers and the real line from numbers to points. Now we'll look at the fact that real numbers are ordered. And you can see that from the line, but we can say even more. So, R is ordered. That means that some numbers are bigger than other numbers. It's a very commonsensical idea. And as I said before, see the line. I guess I could stop there and say that's all there is to it. But I want to introduce a notation. So let me show you something. We can take the real numbers and we can write them a new way. We can write them in this way. We can say that they are the set of all the positive numbers. Now that includes all the numbers we've seen that happen to be positive. 0, that dividing number, and then all the negative numbers. Now those are 3 sets that we've joined together to make the real numbers. And the reason I brought this up is for the following. Definition. Suppose we have 2 numbers, A and B, and suppose they're in the real numbers. So we have 2 numbers in the real numbers. We are going to say the following. We're going to talk about which one's bigger. We will say that A is greater than B if A minus B is positive. Now think about what that means. A minus B is positive only if A is bigger than B. When you take away B, you have something left over. Well, that's what we want this to say. We want this to mean bigger. The way the notation works is you have this angled shaped object. The big side, the open side, is where the big number goes, and the point, the small side, is where the small number goes. Let's go ahead and continue this. A equals B if A minus B is, well, if they're equal, and you subtract one from the other, you should get 0. And so you do. And finally, A is less than B if, now this time B is the bigger one, so where will A minus B be? If B is the bigger one and you subtract it from A, you're going to get a negative result. So here is the way you can describe numbers. One of these three properties will always hold when you have any two numbers out of the real numbers. In other words, we have order. The real numbers have order. Any two numbers, one is bigger than the other, or they're equal. All right. Well, with that in mind, let's extend that notation a bit. Likewise, there's another notation we like to have. We will define A greater than or equal to B. And you heard me say it, and that's what it is defined to be. This means A is greater than B, or possibly A is equal to B. And we put it together in a single nice compact notation. We also can define A is less than or equal to B in the same way. This means that A is less than B, or that A is equal to B. So this allows us a little flexibility. All right, it's time to look at some examples here. So, in fact, let's go to a new page so we have plenty of room. Here's an example. X greater than 4. Now this is an algebraic statement about numbers. I want to write it using the real number line so I could turn it into a geometric statement. Well, here's my real number line. Here, say, is 0. Let me mark off 4 because that's the number I'm interested in. And I want to represent all the numbers x that are bigger than 4. Now this doesn't include 4. So the way I will do that is I'll put an open dot at 4. That indicates there's no point involved. And then I'll mark off all the points going to the right with a slightly thicker line and an arrow at the end. So this inequality means this picture. This is geometry, folks. This is algebra. By connecting the two, it becomes easier to see what this means. It means all the numbers right above 4 and going off to the right forever. Let me give you another example. It's very important that you visualize these things. Example. Here's another one that's more complicated. Minus 1 is less than x is less than or equal to 3. Now we haven't seen this before. Let me go ahead and explain what this means. What does this mean? This means minus 1 is less than x. That's the left-hand part. And simultaneously, at the same time, x is less than or equal to 3. That's the second part. So both of these things must hold at the same time. Now it's very easy to draw a picture that illustrates this. In fact, it's easier to draw the picture than it is to look at the double inequality here. So the two numbers involved are minus 1 and 3. That's all I'm going to mark. Minus 1 and 3. I don't care about 0. It's not part of what I'm looking at this time. Now I want my x's to be greater than minus 1 and not include minus 1. So I'll put an open dot at minus 1. On the other direction, I want x to be less than or equal to 3, but I do want 3 to be included. So I'll put a closed dot there. So I'll shade that in. And what am I looking for? All the numbers that are in between here. So I'll try and shade this all in so it looks a little thicker. And now this inequality up here is this geometric set. So algebraic idea, geometric idea. That's what you want to try for when you're trying to understand this. All right, there is a warning I want to give you. A warning. And this is very common error, so I want to make sure that you don't do this. The statement that looks like this, the statement that, I'll put it in quotes, say, x is less than minus 2, or x is greater than or equal to 5, okay, which means, let me go ahead and show you the picture. because that'll help you understand what this means. Which means what? Well, it means, let's see, there's the line. There's -2 and there's 5, because -2 and 5 are the two numbers I'm interested in. Less than -2 means that we do not include -2, but we can go less than that, any number less than that, which would be all of these. X greater than or equal to 5, we do include 5, and we go to the right, any number that's greater than that is allowed. So this set is a set in two pieces. Okay? This statement, I'm sorry, I forgot to put the end of my quotes there. The statement x less than -2 or x greater than or equal to 5, which means this picture cannot what? Cannot be collapsed, or if you like the word, rewritten as, and let me go ahead and bring this back so you see what I'm about to do. I have x is less than -2, so you might want to think of x as being in the middle, like it was before in the previous example. X is greater than or equal to 5. It cannot be rewritten this way. X less than -2 and greater than or equal to 5. Because if you think about that for about a minute, you'll see that that's impossible. You're asking for numbers x, which are simultaneously greater than or equal to 5, so numbers that are bigger than 5 or possibly equal to 5, and at the same time less than -2. So it would have to be a number that's both positive and negative, which can't happen. This is nonsense. So, when you see statements as in this earlier example, x is greater than -1 and less than or equal to 3, that has to be very carefully qualified. You have to realize that there are numbers in there, and then draw a picture. If you draw the picture, it's very difficult to make that error. But I wanted to warn you against that. All right. Before we leave this topic of order, sometimes we like to talk about a group of real numbers that are all together on the real line, and they are referred to as intervals. So intervals on the real line. And let me go ahead and show you how we're going to notate this. Notation. Open ends, you've seen from the previous examples, is sometimes we don't want to include the number at one end of an interval. Open ends, where, say, endpoints are not included, as you saw in the previous examples, we will use either an open parentheses on the left or an open parentheses on the right. Similarly, for closed ends, now these are endpoints that will include the point at the end. This is where endpoints are included. We will use another notation, square brackets, or square brackets going the other way. So these are the common accepted standards for this kind of notation. Now, let me describe the intervals. What is an interval? I said it was a set of real numbers. There are in fact going to be 9 types of intervals, depending on what part of the real number line we choose. 9 types. The first group, there'll be 2 groups. The first group will be a bounded group. And you'll see what I mean. For example, the first type of interval will be called an open interval. It will look like this, A, comma, B. We'll write it exactly that way. What will that mean? Look at the picture and you'll see why the notation was invented. If this is the real number line and those are the points A and B. Now I do not want to include A, I do not want to include B, but I do want all of the points that are in between the two. So I'll go ahead and shade this region in here. That is what this symbol in the middle represents. The parentheses indicate that A is not included, B is not included, and A and B are simply the start and the end, and all the numbers in between are indicated by this open interval. Let's go ahead and look at what are called half open, or I guess if you're pessimistic, half closed intervals, so you can call them whatever you like. They will have one end open and one end closed. So suppose A is the open end, B is the closed end, or the other way around. A is the closed end, B is the open end. Now I can draw pictures for both of these also. Mark off A and B, A and B. Now in this first one, I do not want to include A, so I'll put an open hole at A. I do want to include B. See, that's what the square brackets are. It includes B. So I'll shade in B. And then the interval is all the numbers in between, and in this case, including the point at the right endpoint. If I look at this half open or half closed interval, this time I want to include A. So I'll shade in that point, but I do not want to include B, so I'll put an open hole there. And then I'll just shade in everything in between, more or less. And now I have an interval where I include the left endpoint. And finally, as you might expect, if we have open and half open or half closed, we finally should have closed. And that would be square brackets on both ends. And you're probably ahead of me on this one. If this is A and this is B, we want to include both A and B. And we shade in between. And we now have an interval that includes both of the endpoints, the left and the right endpoint. And all of these intervals here, all the ones you see here, are bounded. They don't go beyond A or B in any one of these cases. That's what bounded means. They have boundaries on both ends. Now let's look at the other type, because I've only shown you 4 types here. There are another 5 that I claim exist. These will come under the category of unbounded intervals. So these are unbounded. But before we talk about unbounded, if we are going to have an interval that goes off in one direction forever or in the other direction forever, I need a notation for that. I don't have a notation yet, so let's invent one. We're either going to go all the way off to the right or all the way off, all the way off to the left or all the way off to the right. Well, here's the notation that's used for this. To say go all the way off to the left is to say go to minus infinity. To the right, it's to go to infinity. That can also be written plus infinity if you like. Now before we go any further and there are any misconceptions, these are not real numbers. These are not real numbers. What they are just handy symbols. They're very handy. They will allow us to say, go off to the left without stopping, or go off to the right without stopping. But they are not real numbers. What that means is you can't add, subtract, multiply, or divide them, or do anything that you do with real numbers. So, now I'm ready to write down the last 5 intervals I promised you. So, we can have an interval that includes the left endpoint, but goes off to the right forever. Now you might notice that I've put an open parentheses on the right side. That makes sense because I can't have a closed parentheses there. That would mean I include the last number. But there is no last number. So I have to put an open end whenever there's an infinity around. What would the picture look like for that? Well, if this is A, I am including A this time, and now I'm going off to the right without stopping, unbounded. Similarly, I can start A on the left without including A. So I'll have a picture where it's an open circle and then I go off to the right without stopping. And then similarly I can go in the other direction. Minus infinity indicates go to the left without stopping. B can be included, or minus infinity B can be not included. And these, as you might expect, will look something like this. Draw 2 lines there. There's B in both cases. In the first one I include B and go to the left. In this case I do not include B and go to the left. Now that's 8 of the 9 intervals. What is the last one? Well, the last one is everything. Nobody usually writes this as the last one, but let me indicate it. Minus infinity to infinity. What would this look like? Well, that's it. Everything. All of R. Now, if you want to write all of R, usually you write simply R. You don't write the interval. But it's nice to know that it can be included in this notation that we've got. So, having this new notation, we can rewrite what we did in previous examples. So, previous examples, just to show you how this can be used, can now be rewritten as the following. Now, this is a nice way to see that this notation is compact. One of the examples I talked about x greater than 4. This means that x is in the set, the interval from 4 to infinity. Greater than 4 means I do not include 4. That's why I have the open parentheses on the left. And greater than 4 doesn't have any boundary, so I go off to infinity. Here's another one from before. I had minus 1 less than x less than or equal to 3. What is that going to mean? That means x is in the interval open minus 1, because I'm not including minus 1, and on the other end including 3. So this is a half open or half closed interval, including 3. And my final example, x less than minus 2, or, remember, x greater than or equal to 5, that means that x is in the first one. X is less than minus 2. That's going to mean going from minus infinity to minus 2 open, or, because x can't be in both at the same time, remember, x is greater than or equal to 5, x in the interval starting and including 5, so it's closed brackets, square brackets, going off to infinity, to the right. So there I've rewritten the answers to those previous problems in this nice, compact interval notation, which you will see for the rest of the course. So, with that, let's pause for a moment so you can practice some of these real number facts. Now let's continue our exploration of the real numbers by looking at the real line, distance between points. First of all, we're going to make it very simple. We're going to talk about the distance from 0, one particular fixed point on the real number line. So let me show you what I mean. Here is the real number line, and here somewhere is 0, which is the origin, if you recall. Now suppose we have a number on the line, say I'll write it to the right, the number a. Now it has a certain distance from 0. We're going to give that distance a name. But before I do give it that name, I want to point out that there's another number that is the same distance from 0 as a is. If we just go to the left of 0, to right about there, the same distance a, we come up to the number minus a. Now minus a also is the same distance away from 0. So both of these numbers are the same distance away. So with that in mind, we're going to define what that distance is. Definition. See, before we talk about the distance between two arbitrary points, we're going to take the distance between a number, an arbitrary number, and a fixed point, the 0 point. And here it is. The distance from a real number x, okay, we'll just call it x this time for the time being, to 0, which is the origin, is called, now this is a name that probably could be better, but we'll give you the name. This is called the absolute value of x. Now I'll put underneath it what we probably should have called it. It should probably be called the absolute distance. I'll put that in quotes because you won't see that anywhere. You'll see absolute value. But we probably should call it absolute distance because it's simply the distance of this number from 0. And it's called the absolute value of x, and how do we denote it? It is denoted as follows. Absolute value of x. Two parallel lines on either side of x. So let me show you some examples so you'll see how this notation is used. Now remember what this is. This is the distance of x from the origin, from 0. Here's an example. Suppose we have this situation. Here's 0, here's 5. This distance here is the absolute value of 5 because it is the distance 5 is from 0. Now we can actually calculate that because we know how far away 5 is. It is 5 units away. All right? Maybe you think that was too easy. How about this? Suppose 0 is here and we go to the left to say the number -4. Now this is the distance of -4 from 0, the absolute value of -4. What distance is that? How many units do you walk to get to -4? Well, of course you walk 4 units. So the absolute value of -4 is 4. We're developing a theory on how to use this notation, aren't we? We're seeing that if you're to the right, then the absolute value of you, your distance from 0, is indeed just yourself, the positive number. If you're to the left of 0, it looks like the leftward indicator needs to be removed. And you just write the absolute value of -4 is simply 4. Now that's a bit colloquial. Let's go ahead and write down what we seem to have discovered. Another way of writing down what that symbol means. So, this symbol, the absolute value of x, which remember we might think of as the absolute distance of x. That is to say, the distance of this number from the origin, 0. Our experience suggests the following. It's the same thing as x, whatever's inside there, if x is a positive number, if x is to the right of 0, x is greater than 0. If x is 0, well, of course, what's the distance of 0 from itself? 0. So if x is 0, then the distance should be 0. And then, first I'll write the if part. What if x is less than 0? That means left of 0. Well, as we found out with the absolute value of -4, let me bring that back and show you, the absolute value of -4 turned out to be simply 4. The minus had no bearing on it. Well, how would one get rid of a minus? Well, you know from your experience with negative numbers that if you take x, x is less than 0, so it has a minus or a negative internal to it. By putting another minus out front, that will make it positive and give us the absolute value or distance. Because distance, after all, should be a positive number. So, just to write it out again, this is the absolute value of x. I've also called it the absolute distance, where by distance I mean distance from 0. And you might just call it that, distance of x from 0. Now we will explore throughout this course other situations where the absolute value is used. But if you remember this fundamental idea that is a distance measure, it will make all of those calculations easier. Now that we have distance between an arbitrary point and 0, let's worry about what the distance would be between 2 points, where one of them might not be 0. So the distance between 2 points on the real line. Get that all down there. All right. And the 2 points may not include the origin, so we might have something new. Well, what I'll do here is we'll explore this again by example, and I think we'll see how this is going to work. So suppose we have, maybe 0 is there, and we have 2 numbers, -3 and 5. And since I also want to refer to the points, remember these are numbers, so they are algebraic objects. Suppose I want to refer to the points where these numbers occur. Let me call this point P and this point Q. It'll make things a little easier later. Then I ask myself, what is the distance between those two? The distance. Well, it's very easy to see, even though this is not to scale, clearly, that if I go 5 to the right, there's 5 units involved, and then I go 3 units to the left, the total number of units is 8. So the distance between these 2 points is 8. Now let's see if we can figure out a way to write that using the notation that we have. Notice, based on that picture, let me even redraw it. So here's -3 and 5. All right, here's 0 in here. Notice the following. If I take the absolute value of the difference of the 2 points, minus 3 minus 5, or if you like, the absolute value the other way, 5 minus the minus 3. Watch what happens. Minus 3 minus 5, as you know, adds up to minus 8. And how far is minus 8 away from 0? Well, 8 units. On the other hand, 5 minus a minus 3, that's 8 inside these absolute value lines. And how far is 8 from 0? Also 8. So it looks like I might have an aha moment here, and I might have something I can use as a definition. So let me take that idea and write down what I think is a good definition. Definition. If I want the distance between the points P and Q, and for the sake of argument, let me draw them again up here. Here's P, say. Here's Q, and maybe the number associated with P is A. The number associated with Q is B. I could say that that's the absolute value of B minus A, or if I like it the other way, the absolute value of A minus B. Remember, in the previous example we saw that it didn't matter which way I did it, I got the same distance. So that would be the same as saying this is the distance from Q to P, measuring the other way. Because it doesn't matter which way you measure it, it should be the same number. And so that's what we'll do. We'll take this, or like this, either one of these, as the definition of the distance between 2 points. So for example, just to toss in one final example, if I want the distance between, say, minus 11 and 42, I simply take the absolute value of the difference. And it doesn't matter which way I do it. Minus 11 minus 42 will work. What is that? That's the absolute value of minus 53. And how far is minus 53 from 0? 53 units. And there's the distance I was interested in. So that's all that's involved in finding the distance between 2 points on the real number line. Real numbers as decimals. Reals as decimals. Now, decimal numbers have been around for a very long time. Nowadays, they're a lot more common because we use calculators a lot. And so the numbers that we look at often appear in decimal form. You should know some basic ideas about real numbers written as decimals. So let me see if I can outline a few of those ideas. For example, let's look at, first of all, rational numbers, rationals. All right? We'll see what they look like in decimals and see if we can detect something, a principle here. Also, let me remind you, what does decimal mean? Well, the part that says deci refers to base 10. That refers to 10. So we're talking about a base 10. That's where we have the digits, remember, 0, 1, 2, up to 9. So I'm going to know about what rationals look like in decimal form. So let me take a simple rational like 3/4. Now, how do I put this in decimal form? You may remember that the idea is to do a long division. So let's go ahead and walk our way through this. Let's divide 4 into 3. And let's see if we can resurrect some of your experience. I'll put a decimal point after 3 and a couple of zeros. I don't know how many I'll need, but that'll do for now. I can add more if I need them. And then I ask myself, what would I multiply by 4 to get 3? Well, I can't. There is no number. So I then look at 30, and I ask myself, what could I multiply by 4 to get 30, or close to it? Well, I will put a decimal above the decimal that is underneath. Multiplying 4 by 7 gives me 28. If I then subtract that number from 30, I have a remainder of 2. I bring this 0 down, and I have a new number, 20. This is the way the algorithm for long division works, if you recall. Now, I keep this up until I end up with a repeating set of digits up here, or I stop. Now, watch what happens next. I have 20 here. What could I multiply by 4 to get 20? Well, 5 will do the trick. 5 times 4 is 20. I then subtract that away, and I'm left with nothing. So I can stop there. But I can also think of this as now a trivial division, because all the other numbers will be 0. So what do I have? I have that 3/4 is equal to 0.75. But what I really have is 0.7500 dot dot dot. The zeros repeat. So I have what apparently is repeats. Okay? Now that's the first observation. Let's go ahead and look at a little more complicated number. It doesn't look that bad when we write it down, 1/7. But when we do the long division, it takes a little effort. So I wanted to work through one long one to give you a sense of how this works. So I'm going to divide 7 into 1. Well, that can't be done, so I'll put a dot there, and then I'm going to need a few zeros. I don't know how many. Let me just write a few of them there. Put a decimal point above. Now I realize that if I multiply 7 by 1, I get 7. If I subtract that away from the 10 above, I end up with 3. Then I carry the 0 down, I have 30. Now I repeat the process. 4 times 7 will give me 28. If I subtract that from 30, I get 2. Bring the 0 down, I have 20. Multiply 7 by 2, I get 14. With a 6 remainder, bring the 0 down, I have 60. Bear with me. If I multiply by 8, I get 56. Subtract that away, I get 4. Still going. Bring a 0 down, 40. If I multiply by 5, I get 35. Subtract that away, I get a 5 left over. Looks like I'm going to run out of zeros in a minute. 50. And then I multiply by 7. 7 times 7 is 49. I subtract away 49 and I get 1. And now I recognize something. Notice that the first thing I worked with was a 1, and now I've repeated. So now with 1, and then bringing another 0 down, I'm going to have 0. If I subtract away 7, I'm going to repeat the process I just repeated here. So it looks like, although I have 6 different numbers, that's not going to change forever. This is now going to repeat. So I'm running out of space here. Let me write that down a little more compactly. So 1/7 is equal to 0.142857, and then that repeats forever. Now you may remember a compact way of saying that that repeats forever is to put a bar over those 6 numbers. That means that this just continues to repeat. So once again, we have that this repeats. Well, that's only 2 examples, but that certainly does suggest something. In fact, the following fact is true. Rationals have the following property. Rationals, say Q, using that notation, is the set of repeating decimals. You take all the decimals that repeat, including the ones that seem to end. Remember, we looked at 0.75, which was 3/4, and you might say, well, that's not a repeating decimal. Well, sure it is, if you consider the repeating number to be 0. So repeating decimals include and are exactly equal to the set of all rational numbers. Well, it makes it easier to guess what the set of irrationals might look like. The set of irrationals, which doesn't have any standard symbol, would be the set of non-repeating decimals. So, for example, in that set of non-repeating decimals is the number square root of 2, which is a famous irrational. It starts off 1.41423, or 213, excuse me, etc. There's another famous irrational, pi, which you probably know, 3.14159 dot dot dot. Now, I'm not going to kid you, it is difficult to tell if a given number is an irrational number or not, because you have to determine somehow that the decimals don't repeat. And no matter how many you write out, that's not enough to check that. So determining whether a number is irrational or not is a difficult problem. But this at least gives us a way of categorizing rationals and irrationals. One final thing before we leave the real number system. I want to point out an ambiguity. So let me go ahead and write that down. This is another warning. And this will be the last thing I say about the real numbers today. Warning. An ambiguity of decimals. This is a situation where the numbers that you think are always going to stand for the same thing don't. And it's a little surprising if you've never seen this before. I'll do this by example, so you'll see what I'm going to deal with. I am going to show you that 3.999, where the 9's go out forever, is exactly the same number as 4.000 out forever. These are the same number. They look different, and you might suspect that they are different based on that. But in fact, they are the same number. How will I do this? Well, I'll do a verification, meaning I will show you a little calculation that I hope will prove to you that these are the same. All right, starting at the top of this page, let x be the 3.999 out to infinity number. In fact, I'll box that in. What I'd like to end up with at the bottom of my page is that x is also equal to 4. That will show you that those two numbers are the same. Here's the way the argument goes. Then, multiply x by 10. You will get 10x on the left. On the right, what happens? Well, you remember from decimals, when you multiply a number that's in decimals by 10, it moves the decimal point over by 1. So this becomes 39.999. The 9's still go out forever. Now, from this 10x, let me subtract the x number, which is 3.999 out forever. On the left of this, 10x minus x gives me 9x. On the right, 3 from 39 gives me 36, and the 0.999s cancel each other out. They subtract away. So 9x equals 36, x equals 36 over 9, but 9 goes into 36, so x equals 4. And look at that. X started out being 3.999, and now I've got x equal 4. That means those two numbers are the same. Surprisingly. So that's an ambiguity of our decimal system, where two numbers can appear to be different. It only happens in this specific case, where there's an infinite number of 9's. But it is enough to give you pause. Let me show you one more example, and then we'll stop talking about real numbers. Another quick example looks like this, just to show you what can occur inside a number. 0.7321599999 out to infinity. This is going to be the same as 0.73216000. So the 59 becomes a 60. And so these two numbers are the same even though they look different. And of course you'd like the second one better because you can call it a decimal that has zeros at the end, so you can stop it after the 6. You don't have to worry about rewriting the 9's forever. All right. Well, that's all I'm going to say now about real numbers. It's time for you to do a little work and practice with some of the concepts about real numbers.